66 million years ago, the world was perfect. Not perfect by human standards. Not safe. Not gentle. Not peaceful. But perfect in the way that only a fully functioning, deeply balanced ecosystem can be. Dinosaurs had ruled the Earth for 165 million years. To put that in perspective, the entire existence of our species, from the first Homo sapiens to this moment, spans roughly 300,000 years. The dinosaurs ruled for 550 times longer than that. They were not a failed experiment. They were the most successful large animals in the history of life on Earth. And then, in the space of a single day, almost all of them died. Not slowly, not gradually, not over millions of years of climate change or evolutionary pressure. In one day. Today we reconstruct that day. Minute by minute, hour by hour, using everything modern science has revealed about the most catastrophic single event in the history of complex life on Earth. This is the day the dinosaurs died. Part 1, The World Before. To understand what was lost, we need to understand what existed. It is 66 million years ago. The date, as precisely as scientists can calculate it, is approximately what we would call late spring in the northern hemisphere. The world is warm, considerably warmer than today. There are no polar ice caps. Sea levels are higher. The continents are in slightly different positions. North America and Europe are closer together, India has not yet collided with Asia, and the Atlantic Ocean is narrower than it is today. The atmosphere contains more carbon dioxide than today, making the planet a greenhouse world. Forests stretch from what is now Alaska to Antarctica. Flowering plants, a relatively recent evolutionary development, are spreading across the landscape, filling the world with color for the first time in Earth's history. And in this world, the dinosaurs are everywhere. In what will become North America, Tyrannosaurus rex stalks the forests and floodplains. Triceratops grazes in vast herds across open landscapes. Edmontosaurus, a large duck-billed dinosaur, migrates in groups of thousands. Ankylosaurus, armored like a tank, moves slowly through the undergrowth. Pterosaurs, flying reptiles with wingspans reaching 35 feet, ride the thermal currents above. In the oceans, mosasaurs, enormous marine reptiles up to 50 feet long, rule the seas. Plesiosaurs hunt in the shallower coastal waters. The oceans are warm, rich, and teeming with life. Nothing in this world has any warning of what is coming. Nothing in this world has any concept of what is coming. Because what is coming has never happened before in the experience of any living thing. Part 2, The Object. It has been traveling for a very long time. The object that will end the age of dinosaurs is a chunk of rock and metal roughly 6 miles wide. Some estimates place it closer to 9 miles wide. It is not a perfectly round sphere, it is irregular, jagged, ancient. It formed in the early solar system, more than 4 billion years ago. It has been drifting through space ever since, occasionally nudged by gravitational interactions with other bodies, slowly, over millions of years, finding its way onto a collision course with Earth. It is traveling at approximately 43,000 miles per hour. That is 12 miles every second. As it enters Earth's atmosphere, it does not slow down significantly. The atmosphere is not thick enough to meaningfully decelerate an object of this size and speed. What the atmosphere does do is compress in front of the object, superheating it to temperatures hotter than the surface of the sun. The object begins to glow, then to burn, then to partially disintegrate at its leading edge. But its core remains intact. 6 miles of rock and metal, screaming through the atmosphere at 12 miles per second. The entire passage through the atmosphere, from first contact to impact, takes less than 2 seconds. 2 seconds. Part 3, The First Second, Impact. The object hits what is now the Yucatan Peninsula of Mexico. The specific location is now known as Chicxulub, a name that has become one of the most significant words in the history of paleontology. At the moment of impact, several things happen simultaneously that are almost impossible to describe in terms that convey their true scale. The energy released in the first second of impact is equivalent to approximately 1 billion nuclear bombs detonating simultaneously. Not one, not 1,000, not a million, 1 billion. The rock beneath the impact site does not just shatter. It vaporizes. The asteroid itself vaporizes. The rock around the impact site, granite and limestone that has existed for hundreds of millions of years, turns instantly to superheated plasma. A crater begins to form at a speed that defies comprehension. In the first second, the crater is already miles wide and miles deep. The ground beneath the impact rebounds, the rock briefly behaving like a liquid, creating a central peak that momentarily rises higher than Mount Everest before collapsing back. The energy of the impact generates a shockwave that travels through the Earth's crust at the speed of sound through rock, approximately 3 miles per second. This shockwave triggers earthquakes across the entire planet simultaneously. Magnitude 11 or 12 earthquakes, far beyond anything in recorded human history, ripple outward from the impact site across every continent on Earth. Everything within 500 miles of the impact is dead within the first minute. Not injured, not fleeing, dead. The heat, the pressure wave, the ejecta moving at supersonic speeds, nothing survives in the immediate zone. Part 4, Minutes 1 to 10, the ejecta. As the crater forms and the vaporized rock expands outward at enormous velocity, billions of tons of material are thrown into the atmosphere and beyond. Some of this material, molten rock droplets called spherules, is thrown so high and so fast that it actually leaves the atmosphere entirely, briefly entering space before falling back down. The ejecta plume rises hundreds of miles into the sky in the first minutes after impact. It spreads outward from the impact site at thousands of miles per hour. Within 10 minutes, the leading edge of the ejecta cloud has already reached what is now the Gulf of Mexico and is spreading across North America. As the spherules re-enter the atmosphere from space, they do not fall gently. They are traveling at orbital velocities, thousands of miles per hour. And as they pass through the upper atmosphere, they superheat the air around them through friction. The sky begins to glow. Not with fire, not with lightning, with heat. The entire sky, from horizon to horizon, heats up through the infrared radiation generated by billions of rock droplets re-entering the atmosphere simultaneously. Scientists calculate that the thermal pulse from the ejecta re-entry raised surface temperatures across a significant portion of the northern hemisphere to several hundred degrees within the first hour. Everything exposed to the open sky, every animal, every plant, every tree, begins to cook. Forests ignite spontaneously, not because fire spreads from tree to tree, but because the air itself becomes hot enough to ignite organic material. The forests of North America begin to burn simultaneously across millions of square miles. Part 5, the first hour, tsunamis. The impact site is coastal. The asteroid hits shallow water at the edge of what will become the Gulf of Mexico. This location makes the disaster significantly worse than it would have been had the asteroid hit open ocean or dry land. The impact displaces an enormous volume of water instantaneously. The tsunami generated in the first seconds of impact is unlike anything that has occurred in recorded human history. The initial wave is estimated to have been between 1 mile and 2 miles high at its point of origin. It spreads outward from the impact site in all directions at hundreds of miles per hour. Within the first hour, tsunamis reach the coastlines of what is now Texas, Louisiana, Mississippi, Alabama, and Florida. The waves penetrate hundreds of miles inland, carrying ocean water deep into the continental interior. Across the Gulf of Mexico, the waves reflect off coastlines and return, creating a chaotic churning of water that geologists can still see in the rock record today, layers of sediment thrown into impossible configurations by water moving in every direction simultaneously. The tsunamis do not stay in the Gulf. They travel through the oceans in every direction. Within hours, massive waves reach every coastline on Earth. Every coastal environment on the planet, every beach, every river delta, every shallow sea, is devastated. The marine reptiles that rule the shallow coastal seas, the mosasaurs and plesiosaurs, are thrown onto land or crushed against the seafloor by the force of the waves. Marine ecosystems that have been stable for millions of years are destroyed in hours. Part 6, Hours 1 to 6, The World on Fire. By the end of the first hour, the pattern of destruction has been established. What follows over the next several hours is the systematic expansion of that destruction across the entire planet. The wildfires that began in North America continue to spread. But they are not ordinary wildfires spreading through dry fuel. They are burning in conditions that make containment impossible, superheated air, no rain, no moisture, winds driven by the thermal disruption of the atmosphere itself. Within 6 hours of impact, geologists believe that wildfires were burning across much of North America, Central America, and parts of South America. The evidence is in the rock record, a thin layer of soot deposited across the entire planet at exactly the geological boundary that marks the end of the dinosaurs. Soot from fires. Fires that burned almost everything. The sky above the burning continents is black with smoke. Smoke so thick and so widespread that it begins to block sunlight reaching the surface. This is the beginning of the impact winter. But that comes later. In the first hours, the problem is not darkness. It is heat. The combination of the thermal pulse from ejecta re-entry, the burning forests, and the disrupted atmosphere creates surface temperatures that no complex land animal can survive in the open. Animals that can find shelter, underground, in caves, in deep water, have a chance. Animals in the open have none. The largest animals are most vulnerable. They cannot hide underground. They cannot find caves large enough to shelter their bodies. The sauropods, the enormous long-necked dinosaurs that are among the largest land animals ever to exist, have nowhere to go. They die in the open, in the heat, within hours of the impact. The carnivores, T-Rex and its relatives, might survive the first hours better than the herbivores. They are slightly more mobile. They might find partial shelter in dense forest or near water. But the water is toxic, contaminated with sulfuric acid from the impact, and the dense forest is burning. Their options are narrowing by the hour. Part 7, the first day, acid rain. The asteroid that hit Chicxulub did not land on ordinary rock. It landed on a specific type of sedimentary rock rich in sulfur-containing minerals, anhydrite and gypsum. When these sulfur-rich rocks vaporized in the impact, they released enormous quantities of sulfur dioxide into the atmosphere. Sulfur dioxide combines with water vapor to form sulfuric acid, and sulfuric acid falls as acid rain. Within the first day after impact, the most intense acid rain in the history of the planet begins to fall across large areas of the northern hemisphere. Not slightly acidic rain, rain with the acidity of battery acid. This acid rain falls into rivers, lakes, and the ocean. It kills freshwater organisms immediately. It begins the acidification of the ocean surface that will continue for years. It strips nutrients from the soil. It attacks the waxy coating of plant leaves, adding another layer of destruction to ecosystems already devastated by fire and heat. The oceans, which cover most of the Earth's surface and support the majority of Earth's species, begin a process of acidification that will last for tens of thousands of years. Marine organisms with calcium carbonate shells, the plankton, the ammonites, the marine invertebrates that form the base of the ocean food chain, begin to die as the acid dissolves their shells. The ocean food web begins to collapse from the bottom up. Part 8, Days 1 to 7, Darkness falls. By the end of the first day, the pattern of short-term destruction is essentially complete. Everything that is going to be killed by heat, fire, tsunami, and shockwave has been killed. But the long-term killer is just beginning its work. The impact has thrown enormous quantities of material into the stratosphere, the upper layer of the atmosphere above the weather systems. Soot from the wildfires, sulfur dioxide from the vaporized rock, fine dust and debris from the impact itself. All of it rises above the clouds, above the rain, into a layer of the atmosphere where it cannot be washed out by precipitation. And there it stays. For months. For years. Within the first week after the impact, the amount of sunlight reaching the Earth's surface begins to decrease dramatically. By the end of the first week, large areas of the planet are receiving less than half their normal sunlight. Temperatures begin to fall. The short-term heat pulse is over. The long-term freeze is beginning. Photosynthesis, the process by which plants convert sunlight into energy, begins to slow. Without photosynthesis, plants cannot grow. Without plants, herbivores cannot eat. Without herbivores, carnivores cannot eat. The entire food web of the land, every terrestrial ecosystem on Earth, begins to unravel from its foundations. Part 9, Weeks 1 to 4, The Collapse. In the weeks following the impact, the darkness deepens. By 2 weeks after impact, some models suggest that sunlight reaching the surface has been reduced by 90% or more in the most affected regions. At this level of light reduction, photosynthesis essentially stops. Plants begin to die. The herbivorous dinosaurs, already stressed by the fires, the acid rain, and the disruption of their habitat, now face starvation. The plants they depend on are dying. New plants cannot grow without sunlight. The food supply is disappearing. Large herbivores need enormous quantities of food every day just to maintain their body weight. A large sauropod might need hundreds of pounds of plant material daily. As the plant life dies back, the large herbivores begin to starve within weeks. As the herbivores weaken and die, the carnivores follow. Rex and its relatives are opportunistic feeders. They will eat carrion as readily as they hunt live prey. In the immediate aftermath of the impact, there is no shortage of dead animals to feed on. But the supply is finite. And as it runs out, the carnivores face starvation too. The temperature continues to fall as the weeks pass. In what was a warm subtropical world, temperatures drop toward freezing and below in some regions. Cold-blooded animals, which includes most dinosaurs in the traditional sense, cannot regulate their body temperature. As the environment cools, they cool with it. Their metabolism slows. Their movement slows. Their ability to find food and escape danger diminishes. The world that had been perfect 66 million years ago is, within a month of the impact, becoming unrecognizable. Part 10, Months 1 to 6, The Dying. The months following the impact are a period of progressive, cascading death. The non-avian dinosaurs, every species from the mighty T-Rex to the smallest feathered theropods, are dying out. Not all at once, not instantly, but steadily, inexorably, with no possibility of recovery. The large species go first. They need the most food. They have the smallest population sizes. They reproduce the slowest. A T-Rex female might lay a clutch of eggs once a year. Recovery from population stress requires time and resources that no longer exist. The medium-sized species follow. The smaller species hold on longer. Some of them may survive for months or even a few years in isolated refugia where conditions are slightly less severe. But the food web is broken. There is no path back. In the oceans, the collapse is equally total but follows a different pattern. The plankton, the microscopic photosynthesizing organisms that form the base of the marine food web, die as sunlight disappears and the ocean surface acidifies. Without plankton, the small fish that eat them starve. Without small fish, the larger fish starve. Without larger fish, the marine reptiles, mosasaurs and plesiosaurs, starve. The ocean ecosystem collapses from the bottom up over the course of months. Ammonites, the spectacular spiral-shelled cephalopods that have existed for 400 million years, that have survived every previous mass extinction, that have filled the oceans in countless forms since before the dinosaurs existed, finally meet their end. The last ammonite dies somewhere in an acidifying ocean, in the darkness of an impact winter. After 400 million years. Gone. Part 11, The Survivors. In the midst of all this death, some things survive. The survivors share certain characteristics. They are small, small enough to shelter underground or in burrows where the thermal pulse cannot reach them, and small enough to survive on minimal food during the years of darkness. They are generalists, able to eat a wide variety of food sources including seeds, insects, and carrion rather than depending on a single food source that may disappear. They are reproductively flexible, able to produce offspring quickly when conditions improve. The mammals of the late Cretaceous are mostly small, burrowing, nocturnal creatures. They have been living in the shadow of the dinosaurs for 165 million years, never able to grow large, never able to dominate the daylight world where the dinosaurs rule. In the darkness and cold of the impact winter, their small size and burrowing habits become survival advantages rather than limitations. They eat insects. They eat seeds that lie dormant in the soil. They eat the dead. They survive. The crocodilians survive, hiding in river bottoms, able to go months without eating, their low metabolic rate a life-saving adaptation in a world with no food. The turtles survive, similarly low metabolism, able to shelter in mud and water, able to fast for extraordinary periods. The snakes survive, cold-blooded but small enough to shelter and flexible enough in their diet to find food in the devastated landscape. And the birds survive. The birds, which are, in the most precise scientific sense, a lineage of dinosaurs, carry the dinosaur. Legacy forward through the catastrophe. Small, feathered, able to fly to find food across vast distances, able to eat seeds and insects and anything they can find. The birds make it through. And in their survival, they carry something of the age of dinosaurs forward into our world. Every time you hear a bird sing, you are hearing the descendant of the creatures that ruled the earth for 165 million years. Part 12, The World After. The years following the impact are a world transformed beyond recognition. The impact winter, caused by the soot and sulfur dioxide blocking sunlight, lasts for approximately 2 to 3 years in its most severe form. Global temperatures drop by an estimated 10 to 15 degrees Celsius. The warm greenhouse world of the late Cretaceous is gone. After 2 to 3 years, the soot begins to settle out of the atmosphere. Sunlight begins to return. Temperatures begin to rise again. The surviving plants, whose seeds lay dormant in the soil through the years of darkness, begin to germinate. Ferns are the first plants to return in large numbers. Fern spikes are visible in the fossil record immediately above the impact layer at sites around the world, a fern prairie covering the devastated landscape. The surviving mammals emerge from their burrows into a world with no large predators, no competition for the daylight world, and an abundance of ecological opportunities that have never existed before. For the first time in 165 million years, mammals can grow large. Can occupy the daylight world. Can diversify into every available ecological niche. And they do. Within 10 million years of the impact, an instant in geological terms, mammals have diversified into thousands of new forms. Large herbivores fill the role vacated by the sauropods. Large carnivores fill the role vacated by T-Rex. The world rebuilds itself around its survivors. Within 25 million years, a lineage of mammals in Africa is beginning to show the first signs of what will eventually become the primate order. Within 60 million years, the first recognizably human-like creatures are walking on 2 legs. Within 66 million years, one species of primate is building cities, writing books, launching rockets, and making videos about the day their world was made possible. Us. We exist because of the asteroid. We are the inheritors of the catastrophe. Part 13, How We Know. The evidence for the Chicxulub impact is one of the most complete and compelling cases in the history of science. The crater itself, 93 miles wide and buried beneath the Yucatan Peninsula and the Gulf of Mexico, was discovered in the 1970s by geologists working for a Mexican oil company. They did not know what they had found at first. It was only when scientists began connecting the crater to the mass extinction boundary that its significance became clear. The iridium layer is perhaps the most famous piece of evidence. Iridium is extremely rare in the Earth's crust but relatively common in asteroids. In 1980, physicist Luis Alvarez and his geologist son Walter Alvarez discovered a thin layer of iridium-enriched clay deposited at exactly the geological boundary between the Cretaceous and the Paleogene, the boundary that marks the end of the dinosaurs, at sites around the world. The only explanation for a global layer of iridium at exactly the right time was an asteroid impact. Shocked quartz has been found at the boundary layer at sites worldwide, quartz crystals deformed by the extraordinary pressures that only occur during meteorite impacts or nuclear explosions. Spherules, the tiny glass beads of molten rock thrown into space and rained back down, have been found at the boundary layer across North America. Soot from the global wildfires is preserved in the boundary layer at sites on every continent. The evidence is global, consistent, and unambiguous. At exactly 66 million years ago, a rock from space hit the Earth at Chicxulub. And the world was never the same. Closing. 66 million years ago, on a warm spring morning, a Tyrannosaurus rex lifted its enormous head and looked at a sky that was perfectly blue and perfectly normal. It did not see what was coming. Nothing did. 2 seconds later, the sky was no longer blue. And nothing on Earth would ever be the same. What followed was 30 minutes of events so catastrophic, so complete, and so total that 3/4 of all species on Earth ceased to exist within a few thousand years. The age of dinosaurs, 165 million years of evolutionary triumph, ended not with a whimper but with the loudest sound ever made on the surface of this planet. And from that ending, our beginning. The small, frightened, burrowing creatures that survived the darkness and the cold and the years of famine, they were our ancestors. They made it through. Against all odds, through the worst catastrophe since the formation of the Earth itself, they made it through. And their survival, in the fullness of geological time, led to us. We are here because of what was lost. We exist in the space that was cleared for us by an asteroid that had no idea what it was doing. And perhaps the most humbling thought of all, we are the first species in the 4.5 billion year history of this planet that can look up at the sky and actually do something about it. We can track the asteroids. We can calculate their trajectories. We can, with enough warning, deflect them. NASA's DART mission in 2022 proved that we can change the course of an asteroid by crashing a spacecraft into it. The dinosaurs had no warning. They had no science. They had no choice. We have all three. Whether we use them wisely, whether we take seriously the responsibility of being the first species capable of preventing a mass extinction, is the most important question our civilization faces. Not because an asteroid is coming tomorrow, but because one will come eventually. And when it does, we will either be ready, or we will join the dinosaurs in the fossil record. The choice, for the first time in the history of life on Earth, is ours.